In this video, we're solving problem 19 from section 14.6 from the Larson and Edwards Calculus Early Transcendental Functions textbook, 7th edition. We're asked to use a triple integral to find the volume of the solid bounded by the graphs of the equations, and then we're given this picture. Now, this picture is labeled in the textbook, but I wanted to wait until I made the video to label those surfaces for you. So one of our surfaces is given by x equals 4 minus y squared. Another surface is at the bottom here in the xy plane. We're told on that surface z is equal to 0, which we know z equals 0 represents the entire xy plane. And then we're also given this top surface. That's actually part of a plane. And the equation of that surface is z equals x. So it's just the plane z equals x. Now I want to point out a couple of things to you before we go on. Most of the time when we're looking at surfaces in three-dimensional space, we are graphing from this perspective. So we've got the x-axis sort of coming out of the page and the y-axis off to our right and the z-axis pointing up. And that's our standard drawing of our right-handed coordinate system. Now this is still a right-handed coordinate system, but we're looking at it from a different perspective. From this perspective, it's kind of like we're standing over here where that positive y-axis is, and we're looking at it from this direction. So the y-axis is coming out at us, the x-axis is going off to the left, and the z-axis is coming up. So that's going to be really important whenever we come up with the bounds for x, y, and z necessary to set up our triple integral. So we're just trying to find volume. And we'll call this the solid region Q. And the way we find the volume of Q is we do the triple integral over Q of dV. And this dV can be written as dz dx dy or dz dy dx. It can be written in lots of different orders, and we have to have the appropriate bounds over here. If we add up all these little volume pieces, we get the total volume. Okay, so that's the idea. So the most important thing now, in order to set this up and solve it, is to come up with the appropriate bounds for x, y, and z. So let's look at bounds for z first. Z has to go from some bottom function to some top function. Now the bottom function in this case is z equals 0, because we're told that z equals 0 is where this solid starts. And the top function is z equals x. Now in order to come up with the bounds for x and y, we need to sketch the projection of this solid onto the xy plane. And I think we can all see that the projection of the solid is that part, well, the boundary or one boundary of that projection of the solid onto the xy plane is that part of a parabola that's right here and then the y-axis. Now, if I draw this in the xy plane, the traditional way, it's going to look a little different. My y-axis is up here and my x-axis is off to the right. But we can see from this picture, when y equals 0, x equals 4, when x equals 0, y equals plus or minus 2. And so we've got this part of that parabolic cylinder that looks like this, and it's sort of coming out of the page. And then this is intersecting with a plane, z equals x, and it's coming up like this. We've changed our perspective a little bit though. So the positive y-axis is coming out at us, and the x-axis is going to the left. This is what it would look like if we were looking at it from the perspective where the x-axis goes to the right. So this is our region, and we know that the equation of this curve is x equals 4 minus y squared. Now we have choices. We could integrate with respect to y first and then x, or x first and then y. But remember, whenever you do that, the first variable has to go from a function to a function, and the second variable has to go from a constant to a constant. Since I already know the equation of this curve, with x as a function of y, I think it makes the most sense to let x go from a function on the left to a function on the right, while y goes from a bottom number to a top number. So the function on the left is just the y-axis, which is given by x equals 0. And the function on the right is x equals 4 minus y squared. As x goes from here to here, y goes from -2 to 2. That's one way of doing it. If you wanted to, you could let y go from the bottom function here to the top function there, and let x go from 0 to 4. So let's describe this in an alternate way. Do the easy part first. X starts at 0 and goes to 4. But in order to do that, I need to come up with y as a function of x on this curve and on this curve. So I have to solve this equation for y. It's not too difficult. We'll just subtract 4 from both sides, multiply both sides by -1, and then take the square root and make sure you include the plus or minus. So y is the positive square root of 4 minus x when we're up here when y is non-negative, and y is the negative square root of 4 minus x down here when y is negative or possibly 0. So in this case, the bounds for y would be from the negative square root of 4 minus x to the positive square root of 4 minus x. Now you don't have to do this, but some students prefer to always let y go from a function to a function and let x go from a constant to a constant. In this case, since this was given to us, I think it made more sense to do it this way. Either way, if you use these bounds for x and y or these bounds for x and y, you're going to get the correct volume here. Okay, so let's set up this volume integral and evaluate it to find that volume. Now notice that z is going from 0 to a function of x is going from 0 to a function of y, and y is going from a constant to a constant. So if I use these bounds, I have to integrate with respect to y last, and I need to integrate with respect to z before I integrate with respect to x. And then I need to integrate with respect to x before I integrate with respect to y. And then that means that the order of integration is dz, dx, dy. And then you remember how this works. We start in the innermost integral and we work our way out. I've got a 1 dz there. So we're just taking the antiderivative of 1 with respect to z, which is just z, and we evaluate from z equals 0 to z equals x and subtract. At z equals x, we get x. So we're going to end up with x minus 0, which is just x. And then we do the same things, the next integral. Now we're integrating with respect to x. The antiderivative of x with respect to itself comes from applying the power rule. We add 1 to the exponent and divide by the new exponent and evaluate from x equals 0 to x equals 4 minus y squared. At 4 minus y squared, we get 1/2 of 4 minus y squared quantity squared. And at x equals 0, we get 0. So we're just subtracting 0 from this, which just leaves us with this. And now I want to integrate this. Now, if there was a y out here, I might choose to do a u substitution because I've got a function nested inside another function. But there's not a y out there, so u substitution won't work. What we should do then, since u substitution won't work, is use some algebra to simplify this so that we can evaluate the integral. So what we'll do, since we've got a binomial squared, is we'll write it twice in FOIL. Or you can call it distributing if you want, same thing. First times first is 16, outer times outer is -4y squared, inner times inner is the same. So I've got 2 of those, that makes that -8y squared, and last times last is a negative times a negative, which is a positive. Add the exponents, it's y to the 4th. And you can distribute the 1/2 if you want to, or you can just bring it down as a constant. And now we just anti-differentiate this with respect to y. The antiderivative of a constant with respect to y is that constant times y. Bring the -8 down. Then we use the power rule. Add 1 to the exponent and divide by the new exponent. And then we do the same thing here. Add 1 to the exponent and divide by the new exponent. And then we evaluate from -2 to 2. So we have 1/2 of 16 times 2 is 32, minus, we're going to have 8 times 8 over 3, that's 64 over 3, plus 2 to the 5th, that's 2 times 2, which is 4, times 2 times 2 is another 4, so 4 times 4 is 16, times another 2 is going to be 32 over 5. That's all of that evaluated at x equals 2. Or excuse me, y equals 2, and then we want to evaluate the same thing at y equals -2. Notice that all of these exponents are odd, so we're going to get exactly the same answers that we got the first time, but times -1. So we're going to get -32 plus 64 over 3 and minus 32 over 5. And then since we're subtracting that something negative. See what happens if we distribute that negative through just the negative. We actually get 2 copies of the same thing, which is something that we may have realized if we saw that this was an even function and we said, oh, we'll just double it and integrate from 0 to 2, we'll get the same answer. That's why. Okay, now at this point, we could have a lesson in simplifying fractions, but I'm not going to do that to you in a calculus video, not in Calculus 3. I'll just use my calculator to do the arithmetic to save us some time. Okay, so I've got 32 minus 64 over 3 plus 32 over 5, and I get 256 over 15. That's the exact answer. And we're talking about volume, so that's some number of units cubed. So what kind of units? Well, whatever units x and y were originally measured in. X, y, and z were originally measured in. So that 256 over 15, that's the volume of this guy. Now, we evaluated the integral using these bounds, but we could have just as easily evaluated the integral using these bounds combined with this. Z goes from 0 to x. In this case, I would need to integrate, well, either with respect to y or z first, because the bounds for both of them depend on x, and we have to integrate with respect to x last. So this is one way of doing it. The alternate way, or an alternate way, is to let z go from 0 to x, y go from this negative square root to the positive square root, and let x go from 0 to 4. You want to practice your integration skills, you could evaluate that integral instead and see that you get exactly the same thing.